period of satellite. Then period of satellite. That period of satellite which is denoted by capital T. Then this period of satellite, it is also defined as the time taken by the satellite to complete the one revolutions around the earth is known as the period of satellite. When that satellites which are revolving around the earth and complete one revolutions around the earth, at that time, what is the period of that satellite and what is the equation for that period of revolutions? Then again, we have to consider the earth and a satellite of mass small m, which is revolving around the earth at height h with a critical velocity vc, Let us capital R be the radius of this satellite earth and capital M be the mass of the earth. Then satellite which revolve around the earth and complete one revolution, then it covers a distance equal to the circumference of the circle, and that circumference of circle is, that is, twice pi capital R. When that satellite which is revolve around the earth and complete one revolutions, it covers a distance equal to the circumference of the circle, and that circumference of circle is, that is, twice pi in bracket R plus h, but that R plus h is equal to small r, so that the circumference of earth is twice pi r. That is the distance covered by that satellite in one complete revolution. But we know that time is equal to distance upon velocity. That time is capital T, that is period of satellite. Then distance covered by the satellite in one complete revolution is twice pi r, and velocity is vc. But we know that the expressions for the period of critical velocity of the orbiting satellite at height h, that is vc, is equal to under root g capital M upon R plus h, that is equal to under root capital G capital M upon small r. Then that is equation 1, that is equation 2. But we have to simplify this equation, that is putting the value of Vc in this equation, that is Vc is equal to T is equal to twice pi small r divided by under root capital G capital M by r. But T is equal to twice pi small r into small r divided by Zn, and T is equal to twice pi in square bracket, that is r square into r divided by Zn, and T is equal to twice pi in square root that is r cube upon z m. That is the required expressions for the period of orbiting satellite very close to the surface of Earth. But this equation is squaring on both sides. This equation squaring on both sides, that is t square is equal to 4 pi r cube upon z m. But t square is equal to 4 pi upon g m into r square. That is the same equations after squaring on both sides, which is written in the simplified forms. Then we are 4 pi upon z m. We are capital G is that gravitational constant, and capital M is the mass of Earth, and mass of Earth is constant. So that 4 pi upon gm is equal to constant, and then t square is equal to constant into r square, so that t square upon r cube is equal to constant. From these equations, again we have to conclude that then that t square directly proportional to r cube means the square of period of satellite, which is directly proportional to the cube of radius of the Earth. Means the orbit of satellite is large, then period of satellite around this Earth on the same orbit, which is also large. Means the period of satellite which is directly proportional to the cube of radius of the satellite. Again, what is the effect of that acceleration due to gravity on the period of the satellite? Again, we know that acceleration due to gravity at h, that is gh is equal to g capital M upon r plus h bracket square is equal to capital G capital M upon r square. Then gm is equal to gh r cube. Gm is equal to gh r cube, and this equation which is put in the equation, that is t is equal to twice pi under root r cube upon gm, then that is t is equal to twice pi under root r cube upon gm. Means the value of that gm is gh r square, where r square and these two r get cancelled. Remaining thing is, that is t is equal to twice pi under root r by gh. That is the effect of that gravity on the period of the Earth. Then again the effect of density of Earth on the period of this satellite is, again consider the Earth, and Earth is a solid sphere. Then volume of Earth is V is equal to 4 by 3 pi capital R cube, and mass of the Earth is equal to mass of earth is equal to, that is volume into density, that is mass capital U, volume V and density rho. Then put the value of that volume, that is capital M is equal to 4 by 3 pi r cube into rho, and this value of mass of the earth which is put in the equation, that is T is equal to twice pi under root r cube by Gm, means the period of satellite at the height h, that is T is equal to twice pi under root, that is r cube upon value of m g 4 by 3 pi r cube into rho. Then T is equal to twice pi under root, that is thrice r cube upon 4 g pi r cube into rho. Then this twice pi, which is taken in a square root, that is 4 pi square, that is 4 pi square. T is equal to under root, that is 4 pi into thrice r cube upon, that is 4 g pi r cube rho. Here 4 get cancelled, pi get cancelled, and remaining thing is T is equal to under root, that is thrice pi r cube upon capital G r cube into rho. That is the terms, the period of satellite revolving around Earth at height h in terms of the density rho. From these equations, we have to know that or conclude that that is the effect of density of that Earth on the period of the satellites. Then from these equations, we have to also determine the period of satellite very close to the surface of the Earth. Then again, consider the satellites of mass small m. Consider the satellite of mass small m, which is placed on the surface of Earth. Which is placed on the surface of Earth. When any types of the body or satellite which are placed on the surface of Earth, which is stationary or stable, but it does not revolving around the Earth, so that satellite which is revolving very close to the surface of Earth at such instant that h is very less than the r, so that h is negligible. At the same time, again, that satellite which are revolving very close to the surface of Earth, then that satellite which complete a distance, that is twice pi r in one complete revolutions, so that the time is equal to distance upon velocity, and that satellite which revolve very close to the surface of Earth with critical velocity vc, so that time is capital T, distance is twice pi r, and critical velocity of that satellite very close to the surface of Earth is vc. Let us, that is equation 1. But we know that the critical velocity of that satellite very close to the surface of Earth, that is vc is equal to under root g capital M by r square. That is equations 2. Then we have to put the value of vc in above equations, that is t is equal to twice pi capital R upon the value of vc under root g capital M by r square. Then simplify these equations, that is t is equal to twice pi r in bracket, that is r square divided by Gm. But t is equal to twice pi, t is equal to twice pi, which r is taken inside that critical equation of the critical velocity very close to the surface of Earth, not under root Gm by r square, but vc is equal to under root Gm by r. So that this equation is t is equal to twice pi r under root r by Gm, and that capital R outside this square root, which is taken inside the square root, that is r square into r upon Gm, and then this required expression t is equal to twice pi under root r cube by Gm. That is the period of satellites very close to the surface of Earth. Again, then what is the effect of that acceleration due to gravity on the period of satellite very close to the surface of Earth? Then we know that the acceleration due to gravity on the surface of Earth is, that is g is equal to g capital M by r square, and this equation is simplified for Gm, that is Gm is equal to gr square, and this value which is put in the equation of period, that is t is equal to twice pi under root r cube by Gm, then t is equal to twice pi under root, that is r cube upon g by r square, where r square and these two r get cancelled, and remaining thing is, that is twice pi under root r by z. That is the equation for that period of satellites in terms of that gravity. Then from these equations again there is some effect of density of the Earth on the period of satellite very close to the surface of Earth. Then again we know that the mass of Earth is equal to volume into density, that is capital M is equal to V volume and density rho. But we know that the volume of earth V is equal to 4 by 3 pi r cube into r cube. Then put the value of V in this equation, that is M is equal to 4 by 3 pi r cube into rho, that is the mass of earth. And this mass of earth which is put in equation, that is period of satellite very close to the surface of earth, that is T is equal to twice pi under root r cube by ZL. Then that T is equal to twice pi under root r cube upon Z, and value of M, that is 4 by 3 pi r cube into rho. Then these equation which is simplified, that is T is equal to twice pi under root, that is thrice r cube upon 4z pi r cube into rho, and T is equal to twice pi under root, then we are r cube get cancelled, thrice by 4 into 1 by, that is g pi rho. Then we have to take the square root, taking the square root of the 4, or these twice pi which is taken into the square root, that is T is equal to under root, that is thrice into 4 pi square upon 4 z pi rho. We have 4 get cancelled and pi get cancelled. Then remaining thing is T is equal to under root thrice pi z rho, thrice pi z rho. That is the required expression for the period of satellite very close to the surface of earth in terms of the periods.